Bismillah ar-Rahman ar-Rahim. Hello everybody. Today, inshallah, we are going to start our third tutorial, which is about regarding chapter 4, which is talking about the resultant or force system resultants. Okay, and we are going to introduce the topic of moments in 2D, 3D, the couple of moments, and simplification of the resultant of a system. As usual, just as a quick overview, the moment if we are dealing with a 2D problem, it's easier to use scalar analysis. Okay, so we're going to say the force multiplied by the distance, which is the perpendicular distance from the point till the line of action to the of the force. And we can say that if it's counterclockwise, acting counterclockwise, it will be positive, and if it is acting clockwise, it will be negative. But if we are dealing with a 3D problem, it's much easier to use the vector analysis. Okay, so we are going to use ij and k hat terms. So in the vector or in 3D problems, we are going to say the moment is equal to, okay, the distance or the position vector multiplied by the force. Okay, so if we are using that determinant, you can say here it's I hat, j hat, and k hat. And here it's the x component of the position vector, the y component, and the z component. Okay, and here fx, fy, and fz. Or we can use also this I, j, k, and this is the positive like sign convention. So if we are saying I cross product j hat, we will get what? K hat. But if we say j hat multiplied by I hat, we will get what? Minus k hat. Okay. What if we say like I cross product I? It will be 0. Why? Because the cross product, if we say like A cross product B, okay, the result will be what? Will be the magnitude of vector A multiplied by the magnitude of vector B sine theta. So the angle between I hat and I hat is 0, so sine 0 is 0, okay? And the direction, so let's say here it's the vector A, and here it's the vector B, okay? So the direction will be what? Perpendicular to the plane containing A and B, okay? So it's perpendicular to both A and B, the plane containing A and B vectors. Okay, so let's begin our first problem here. It's given the pipe assembly is subjected to the force F, okay, in newtons. Determine the moment of this force about point A. Later, we will explain what if the moment is required about an axis. So here it is about a specific point, okay? So here is the point A, and here is our force F. And the position vector R will be from the point A, okay, till any point located, which is located on the line of action of the force. So we can say here it is RAC, or if this point is B, okay, we can say RAB, okay, we can say RAB. Okay, so it is the position vector R multiplied by F, not F multiplied by R. Otherwise, it will be minus F multiplied by R. Okay. So first of all, we should find here we will use RAC. Okay. So the position vector will be what? Half minus 0 I hat plus 0.7 minus 0 j hat plus minus 0.3 minus 0 k hat. Okay, so we'll get the position vector in meters. Now we can use the cross product since it's a 3D problem. It's much easier to use the cross product. So I, j, and k. Here is our position vector. Okay, and the force is given to be 600 I plus 800 and minus 500. Okay, so here I will start with the I hat, correct? So here it's like the law of the determinant. I will say what? 0.7 multiplied by minus 500 minus this term, which is minus 0.3 multiplied by 800. Okay, so 0.7 multiplied by minus 500 minus this term, which is minus 0.3 multiplied by 800. Then moving forward to the j hat term, we will say what? Here is our j hat term. So I will cancel these and I will say minus. Here it's very important for us to not forget the minus sign. So minus j hat 0.5 multiplied by minus 500 minus this term, which is minus 0.3 multiplied by 600. Okay, and the final term will be what? K hat. So we will say plus k hat, this term, which is 0.5 multiplied by 800 minus 0.7 multiplied by 600. Okay, and we will get the answer. And here the result will be a vector notation or a vector result. Unlike the dot product, as we did in chapter 2, we said that the result of a dot product will be a scalar one, correct? Okay, when we were finding the the component of a force parallel to an axis. So let's move forward to the second problem here. It's saying determine the moment of this force about an axis. So what will be the difference? What will be the difference here? We said that the moment about a point, say for example O, will be what? R multiplied by F, correct? And the answer will be what? A vector. But if they are saying like about an axis as we did in chapter 2, we are going to use again the dot product. Okay, dot product to get the value of the moment about an axis, but on a specific axis. So we will say what u, the unit vector of the axis A, say for example, here is the vector, dot product, this MO, which is what? R multiplied by force. Okay, so here the final result will be what? A scalar answer. Okay, the magnitude, the answer will be a magnitude, just a magnitude. And this is called a scalar triple product. But what if we want the vector notation of the moment about the axis? Easily here the answer, as we said, MA is a magnitude. But what if we want the vector? We can say easily, okay, it's magnitude multiplied by what? The unit vector of the axis A. Okay, so here about an axis extending between A and C, express the result as a Cartesian vector. So we will first find the magnitude here, the magnitude, then to get the Cartesian vector notation, we are going to use this equation again. Okay. So here first we have to find what? Here is the position vector R will be what? Any point extending from the axis. So here's our axis, AC. Okay. So R will be from any point till the line of action of the force. Here's our line of action of the force. So the R will can be RCB because it's from the axis till any point which is located on the force. Or we can say again RAB. Okay. because again, RAB, the point A is located on the axis of the moment, and B is located on the line of action of the force. But here it will be much easier if we take the position vector to be RCB, okay? Because it's like in the direction of the Z axis. And here is our the moment axis, okay? So here the result will be scalar, the unit vector of the axis AC dot product, the position vector multiplied by the force. And here R is any position vector from any point on the axis AC till any point passing through F. It could be RCB or RAB, but as we said, it will be easier if we take RCB, okay? And then we will multiply the magnitude by the what? The unit vector of the axis AC, okay? So the position vector RCB is what? Is just 2 meters in the negative z-axis, okay? So 2 minus 2 k hat in meters. And the unit vector of the axis AC will be what? The position vector RAC, here it is RAC over the magnitude RAC, okay? So here see the coordinates is 4, the x-axis is 4, the distance, then 3 meters in the y-axis and 0 meters in the z-axis. And A is the origin, so 0, 0, 0. So it will be 4 I hat plus 3 j hat. So the position vector of AC will be 4 I hat plus 3 j hat over the magnitude to get the unit vector, okay? So finally we will get 0.8 I hat plus 0.6 j hat. Now we are ready to do the scalar triple product. So here is the unit vector multiplied by dot product position vector cross product the force. So UAC is zero point 0.8, okay, zero point 0.8, zero point 0.8, zero point 0.6 j hat, zero point 0.6, and the k term is 0. Then the position vector RCB is what? Just minus 2k hat, correct? Just minus 2k hat. So it is 0, 0, minus 2. And the force is given, correct? Here, 4 I hat plus 12 j hat minus 3 k hat. So 4, 12, minus 3, and we will do the determinant. So here, first of all, get like the I hat term, okay? This will be cancelled out, So we will say 0 multiplied by minus 3, which is 0, minus 2 multiplied by 12, okay? Multiplied by zero point 0.8. Then we will say minus this term, minus this term, so minus zero point 0.6, then 0 multiplied by minus 3 minus 2 multiplied by 4, okay? And finally, plus 0, okay? Plus 0 multiplied by, like, 0 multiplied by 12 minus 0 multiplied by 4. But anyway, here it's 0, so the whole term will be cancelled out, okay? So here it is 0. So the magnitude we will get, as we mentioned, a scalar, because here we have a dot product. So the magnitude will be what? 14.4 kilonewton meters. Now, as the result as a Cartesian vector, we will say again the magnitude multiplied by the unit vector of the axis AC. And the unit vector of the axis AC is what? 0.8 I hat plus 0.6 j hat. Okay? So the result will be a Cartesian vector notation in kilonewtons meter. Now here, like, we have another topic, which is uh, like a couple moment, okay? So here, let's say we have axis, okay? let's say here it is FA, vector FA, and here it is vector FB, okay, and here is point B, and here it is point A. So a couple consists of two forces, two vectors, okay, which is equal in magnitude but opposite in direction, and they are parallel to each other. So the here it's a free vector. The result will be what? Here, if we are using the vector notation, we are going to say either R A B, so R A B multiplied by what? Tip to tail rule multiplied by FB, okay, and we will get the moment of this couple, okay, or we can say what? We can say the moment is equal to RBA multiplied by FA, okay, so RBA multiplied by F. But if we are dealing with a 2D problem, a scalar analysis will be just M is equal to FD, okay? And the D is the distance from the first vector till the second vector. Here is the D, the perpendicular distance, okay? Here it's F1 or F2. It doesn't matter because they have the same magnitude. And the direction, we can easily get it when we are dealing with a 2D problem from the right hand rule, okay? So let's see our problem here. Determine the resulting couple moment. So MR of the two couples. We have two couples, okay, that act on the pipe assembly. The distance from A to B is 400 meters. So here from A to B, D is given to be 400 millimeters. Express the result as a Cartesian vector. We will get by default the result as a Cartesian vector because we are dealing with a cross product, okay? But here the idea is that we have more than one couple moment. So we are going to take the summation for each coupled moment, okay? Here, first of all, we can say RAB multiplied by F1, or we can say RBA multiplied by minus 35 kHz, okay? So it's up to you. Here, I took RAB, and I will multiply it by F1, which is 35 kHz. So first of all, the coordinates here will be what? For point A will be 350 millimeters in the X direction, and it has moved 0 distance in the Y direction and 0 distance in the Z direction. So 350, 0, 0. What about point B? It is again 350 in the X direction, and in the Y direction, this distance will be negative, which is 400 cosine 30 will give us this distance, okay? And regarding the Z direction will be what? 400 sine 30, okay? We'll get this vertical distance in the positive Z axis, okay? So it will be 200. 400 sine 30 is 200, and minus 400 cosine 30 is minus 346.41. Okay, anyway, now we are ready. So RAB, so here RAB, we are going to say the coordinates of point B minus the coordinates of point A. So 350 minus 350 I had plus this component minus 0 plus this coordinate, the Z coordinate 200 minus 0 kHz, okay? And we'll get the answer in millimeters. And here we can notice that we just need one position vector. Why? Because here also regarding F2, which is minus 50 I hat and 50 I hat, okay? The position vector RAB is passing through the line of action of the force F2, okay? Okay. So here again, the position vector is what from the line of action, it passes from the line of action or extends from the line of action of F1 to the line of action of the other force F2. Okay, so here we will say, okay, RAB multiplied by F1. So here RAB multiplied by F1 plus RAB again multiplied by what? By F2. Okay, which is minus 50i, not this force 50i had, because it's a tip to tail load. Okay, so here just we will do the determinant I, J, and K, I, J, and K, and RAB is what? 0 minus 346.41, 200, and here is the same. And regarding F1, it is 35 K hat. So 35 and 0 and 0. And here F2 will be what? Minus 50 I hat. Just minus 50 in the I hat term, 0 and 0. And we will do, okay, I hat, then minus 346.41 multiplied by 35, okay, and the other time minus 200 multiplied by 0, it will cancel out, okay, plus, or we can say what? Minus j hat, okay, 0 multiplied by 35, which is 0, minus 200 multiplied by 50, okay. So here it will be again, it will be 0. So 0 multiplied by 35, it will be 0. Minus 200 multiplied by 0, it's again 0. And regarding the third term, it will be also 0. Why? Here, notice that plus k hat, 0 multiplied by 0 is 0, minus 346 multiplied by 0 is 0. Okay, so from this determinant, we just have this term. Now, from the other determinant, here, okay, we'll say plus I hat, okay, this term will be 0, minus 346 multiplied by 0, minus 200 multiplied by 0 is also 0. So we don't have I hat term. Now, from the j hat term, we'll say, okay, minus j hat, 0 multiplied by 0, minus 200 multiplied by minus 50. Okay, and then finally, the k hat term will be what? Plus k hat, then 0 multiplied by 0 minus 346.41 multiplied by minus 50. Okay, and we will get the result to be uh, as a vector notation. Okay, and the units is in kilonewton meters. Or simply we can use this like this rule. Okay, if we don't want to use the determinant, we will put, okay, here is our RAB vector. So here is our position vector. Here is our F1 and here is our F2. Okay, and we will say, okay, here, first of all, minus 346.41 multiplied by 35 and j multiplied by k hat will give us what? J multiplied by k hat will give us I hat, positive I hat. Okay, then plus 200 multiplied by 35, but it is k hat multiplied by k hat, it will give us 0. Here, 200 multiplied by 35, but it will not make any difference because here k hat multiplied by k hat. Then plus this term multiplied by this term, so minus 346.41 multiplied by minus 50, and j hat multiplied by I hat will give us what? J hat multiplied by I hat will give us minus k hat. Okay, so minus k hat. And finally, positive 200 multiplied by minus 50 and k hat multiplied by I hat. Okay, so k hat multiplied by I hat, k hat multiplied by I hat will give us positive j hat. Okay, and we'll get the same answer. Check 12.11 minus 10 minus 17.3. 12.11 minus 10 minus 17.3. So it's up to you which method you you prefer to use. Okay. Here is like another idea. If we have a system, okay, and we have different forces and moments applied on it, we can replace the whole system by resultant FR, okay, and MR, the resultant moment, okay. So here, the resultant force will be simply the summation of all the forces, okay, and the resultant moment will be what? Summation of all the moments about point O plus summation of all decoupled moments, okay, because they are free vectors. Now, let's see our example here. Replace the loading acting on the beam by a single resultant force and specify where the forces act, measured from point B. Here, to find the location, we are going to use the moments of the resultants and the second term. We can find easily the location of the resultant force, okay? Now here, to find the resultant force or to replace like the loading acting in the beam by a single resultant force, first of all, we are going to find the resultant in the x direction, okay? So FRX will be the summation of forces in the x direction. We have first of all what? 450, 450, this force, cosine 60 will be in the positive x-axis. So here is positive y, and here is the positive x, okay? So positive 450 cosine 60, and here we will have this component will be what? 700 sine 30, so 700 sine 30, and it is in the minus x-axis direction, okay? So minus equals to, this will be what? Minus 125 newtons. This means the resultant of in the x direction is acting to the left, okay? Now doing the same regarding the y direction, we will say FRY will equal to what? Here, this vertical component will be 450 sine 60, and since it's acting downwards, it will be negative because the positive is upwards. Okay, and here we have another force, minus 300, and here the component is acting downwards, which is 700 cosine 30 and minus. So it will be 1296 newtons acting downwards. Now, to get the magnitude of the resultant force, we will say square root minus 125 squared plus the vertical component squared, okay? And we will get the answer, okay? 1302 newtons. Now, the direction, it is in the third quarter, okay? So here we will always take the absolute value, okay? So here it is in the third quarter. So here is our theta, and here is our FR. Okay, here the x component is what? 125, and the y component is 1296. So if we say theta is equal to what? Tan inverse 1296 over 125. Okay, and we'll get the angle to be 84.5. If they are asking from the positive x-axis, we are going to add on it what? 180 degrees. Okay, so we have to draw or determine in which quarter we are like dealing with, or our force is located. Anyway, here to find the second part of the problem, specify where the force acts or the location. Okay, we have to use the resultant of the moments. So here it is like this, asking about point B. Okay, so here is our point B. Okay, And here is our resultant force. I can put it anywhere on the beam. So as we mentioned here, first the resultant of the moment of the resultant force. So the moment of the resultant force about point B is what this will have zero effect since it's passing through point B. So we will have just the vertical components. So 1296 about point B, it will be rotating counterclockwise. So 1296, and here I said it is the distance is x-axis. That is our unknown. Okay. So positive 1296 multiplied by x equals to what here? Equals to, we don't have here any coupled moment. So just summation of all the forces here in the system about point B. Okay. So we are going to say what here? We are done with it, the resultant. So we will be left with the vertical component, which is 450 sine 60 multiplied by this distance, which is what? 4 meters. Check here. The distance is 4 meters till point B. And it will be acting also counterclockwise, so positive. So it is positive. Regarding this force, here it is 700 cosine 30. Okay, and here is our point B, so the distance 3 meters, and it's acting clockwise, so it will be negative. So negative 700 cosine 30 multiplied by the distance, which is 3. Okay, and we shall not forget here that we have a moment which is acting clockwise, so it is minus 1500. Okay, so minus 1500. Now here we are left with one equation, one unknown, and we can get easily the value of x. Now here x, the answer is minus 1.36 meters, which means that the x should be in the opposite direction. So in other words, if I put the resultant force here, okay, and I said here is my x, okay, this will produce a moment which is acting clockwise. So it will be a negative here, and I will get the x to be 1.36 meters. Anyway, we can say, okay, it is just 1.96 meters, but to the right of point B. So first, at the beginning, I assumed it to be here in this direction, but it's actually in that direction, to the right, okay? Now here, replace the loading in the frame by a single resultant force. It's the same idea, okay? By a single resultant force, and specify where its line of action intersects member CD measured from NC. So here is our point C. We have to find first of all, the resultant, FR, then we are going to find like the location or the line of action where it intersects member CD, okay, from the resultant moment, okay, equation about point C, okay. So FR, when we get the resultant force, okay, and the angle, we are going to replace it anywhere here on member CD, okay. And we will say, okay, the resultant moment will be what? This vertical component multiplied by distance, let's say x, because we don't know the exact location of it, equals to the summation of all the forces and the couple moments on that system. So we will find the effect of the moment of this force about point C. We will include also this moment, the effect of this force, and the effect of this force, and we will be left with one equation, one unknown, and the unknown is x, and we can find the location, okay? So the same procedure, first of all, we will find the x component of the resultant force, Frx, okay? Here, we will have just two horizontal or x components from this force. First of all, it will be 250 multiplied by 4 over 5, and it will be negative, okay? And here it is 500 cosine the angle 60 theta, okay? And it's also minus. So minus 254 over 5, this force or this component, minus 500 cosine 60, and the result will be what? Minus 450 newtons. So it is acting to the left, okay? Or we can simply say, okay, I will assume the positive direction to be to the left, okay? And the answer will be positive, and our positive direction is to the left. Anyway, here also, the vertical component in the y direction, it will be what? Here, 500 sine 60 will give us this vertical component, but it will be negative, okay? So minus 500 sine 60, and here we have minus 300, okay, concentrated force, and here it will be minus 250, 3 the vertical over 5, okay? So minus 253 over 5, and it will be 883 newtons acting downwards. So it's again negative and negative, so it will be in the third quarter, okay? It has a magnitude of 883 newtons, okay? And we can simplify the angle theta, okay, which is tan inverse the vertical component, okay, which is what? 883 over the horizontal component, which is 450 newtons. Okay, and here it's the absolute value always. So it's 63 degrees. This angle is 63 degrees. Now to find, as we said, the location x of the resultant force, okay, we are going to say the resultant about point C. So I will put the resultant here along member CD. The the horizontal will have zero effect since it's passing through point C, and just will have an effect, the effect of this vertical component. So 883 newtons multiplied by x, and since it is rotating what clockwise, it will be negative, okay? So minus 883x equals to the summation of all the force and moments about point C for what is given from the original problem, or yes, from the problem. So here we have this force, which is, it will have two components here, the 500 cosine 60 and the 500 sine 60, okay? So the 500 cosine 60 will be rotating what? Clockwise, so negative. Negative, and the distance is from point C till this component is what? 2 meters, okay? So you can check here, minus 500 cosine 60 multiplied by distance 2. And the other component here, the other component is what? 500 sine 60. Okay, here is the other component, and the vertical distance till point C, since it's a 2D problem, so we are using scalar analysis, correct? The distance is 1 meters, and it's acting again clockwise about point C. So it is minus 500 sine 60, since it's acting clockwise, multiplied by the vertical distance, or sorry, the perpendicular distance till point C, which is 1 meters. Okay. Now let's check the other forces or moments that we have. We have here the moment, which is acting what? About point C, counterclockwise, so positive. Okay, so positive 400. Okay, and we have this also, this force, 300 newtons, and the distance is what till point C is 3 meters. It's given from the problem here. Check from this force till point C is 1 meter plus 2 meters. Okay, so it is 300 multiplied by 3 meters, and it's acting or rotating about point C in or clockwise. So it is negative. And finally, we have this vertical component. The horizontal component will be 0, okay? because it's passing through point C. So here it will be 250 multiplied by 3 over 5. Okay. And the distance is what here? It is 3 meters plus 3 meters. Okay, so 6 meters. Okay, and it's rotating about point C clockwise. So minus 250 multiplied by 3 over 5 multiplied by distance, which is 6. And here we are left with only one equation, one unknown, and the unknown is x. So we get x to be 2.64 meters from point C to the right. Okay, so here it's from point C to the right. Okay, so here will be the location of our resultant force. Now here, another example, the building slab is subject to 4 parallel column loadings. Determine F1 and F2 if the resultant force acts through point 12 meters and 10 meters. So here's our resultant force Fr. Okay, here it's 12 meters in the x direction. So here it's 12 meters, and in the y direction it is 10 meters. Okay, chapter 4 has so many ideas. So the resultant Fr, first of all, taking the summation of forces in the z direction, okay, we can assume it to be positive downwards anyway. So we can assume it. We have minus Fr, it's downwards, so minus Fr, and minus F1 plus minus F2 plus minus 6 plus minus 12. Okay, because they are all acting downwards. As I said, we can assume it to be positive downwards, and we can like put these all positive sign, and we will have the same result, because we can divide or multiply the whole equation, okay, on both sides by minus 1. So Fr is equal to F1 plus F2 plus 18. Anyway, to find the location of the resultant force, we will have to sum the moments about the x and y axis. Okay, so we will take the summation of moments about the x axis and the summation of moments about the y axis. Okay, to determine the forces F1 and F2. So here, the summation of forces about the x-axis, we have the resultant. First of all, the resultant is here, correct? Here is our resultant, Fr. So about the x-axis, it will be what? The force Fr multiplied by the distance, which is 10 meters, okay? And it will be the negative x-axis, using the right-hand rule. So minus Fr multiplied by 10. So here it is Fr multiplied by 10, and it is minus, okay? Now the summation of all of the other forces about the x-axis will be what we have here. We have here this 6 kilonewtons multiplied by 12 plus 8, which is 20. So minus 6 multiplied by 20, and also we have this 12 kilonewtons, which is what? 12 kilonewtons multiplied by 8. So the distance here of this force, okay, here you can check the distance from the x-axis till the line of action of the force 12 kilonewton is what? 8. So minus 12 multiplied by 8, and we said here minus 6 multiplied by 12 plus 8, which is 20. So minus 6 plus 20 multiplied by 20, and here we have this force. It will have a moment about the x-axis. So minus F2 multiplied by 20, okay? Cannot see it. It's in the same line of action or the same axis, okay? So 20 multiplied by F2 and a negative sign. So minus f2 multiplied by 20 will get our first equation. Now our second equation will be about the y-axis because we have two unknowns. So two equations, two unknowns, we will be able to find f1 and f2, and that's what's required, okay? But anyway, the summation of forces about the y-axis. First of all, here is our resultant fr, and the distance is given to be 12 meters. Here, the distance is 12 meters. So minus fr multiplied by 12, okay? Or sorry, positive. If we are using the right hand rule, it will be positive, okay? Here, it will be positive. And fr is what? Fr is f1 plus f2 plus 18, okay? So f1 plus f2 plus 18 multiplied by the distance, which is 12, equals to what? All the other forces. Here, 12 kilonewtons, and we have f1 and 6 kilonewtons. F2 is passing through the y-axis, so it will not have any effect. And also, f1 is passing through the x-axis, so it will not have any effect in this equation. Okay, we don't see f1, and here we don't see f2. So we will say here 12 kilonewtons multiplied by 6, which is this distance, okay, plus f1 multiplied by this distance, which is what? 16 plus 6 meters, which is 22, okay, plus 6 kilonewtons multiplied by 22 meters, okay. So here, after doing some simplifications, we'll get our second equation, and we can get easily the results f1 and f2. Now here, determine the equivalent resultant force and couplement about point O. Okay, we can say, like here, take a small piece, okay, and say this dx, okay, and here is the concentrated force dfr, and here the distributed load w, okay. So here we can notice that dfr is what? Omega dx, which is the area. So omega dx, and omega is what? It's given to be x cubed over 3. So dfr will be x cubed dx over 3. So here is our differential element, okay. So taking like the summation of forces in the y direction, we are going here to integrate since we have a distributed load, okay. So fr will be what? The integration of this differential element dfr, okay, dfr, or this dfr, okay. And here the distance is x, here it is dx, and here the 3, it's 3 minus x, because here it's the total distance is 3 meters. And here is our point O, because they are mentioning or requiring from us the couplement about point O. So after finding dfr here, after doing the integration, we'll say, okay, integrate from 0, here it's 0 till point 3, the differential element. Okay, and here is our dfr from the calculator, or we can do it easily, x to the power 4. Then we have 3 multiplied by 4 in the denominator, so we get 12. Okay, from 0 to 3, we'll get 6.75 kilonewtons, the resultant force acting downwards. Now, to find the moment and the couplement at point O, we have to say the resultant about point O equals to the summation of all the forces here, okay? And we will do the integration, of course. So the resultant moment about point O will do the integration, the force, the differential element multiplied by the distance till point O, okay? So here is our force F, and here is our force, sorry, our distance, perpendicular distance till point O, okay? So we will say dfr multiplied by the distance d, which is 3 minus x, okay? And we will integrate from 0 to 3. And dfr we have calculated to be what? X cubed dx over 3. So x cubed dx over 3 multiplied by this distance, and we can find it easily from the calculator, or we can do the math, okay? And since it's positive, it is counterclockwise. By this, we conclude our tutorial, hoping you have benefited from this tutorial, and thank you for your time.